Hey Chem30s, since I can't be there today, I'm going to quickly run you through a lesson on voltaic cells today. This is the second half of the unit for the redox unit, and what we're going to be getting started on today is a look at different kinds of cells that are powered by redox reactions. So hopefully you've done the quick lesson that started off B7 in your notes. If you haven't, it'd probably be a good idea to grab your textbook at some point and get through to that. So what we're going to do is I'm going to introduce you to what a voltaic cell is, what it looks like, how it works, and please pay attention for where redox reactions come into this, because redox reactions are what power voltaic cells. So voltaic cells, also called electrochemical cells. Actually, electrochemical cells is a broader term that refers to both voltaic and electrolytic cells. They're used to get electricity in the form of electrical energy out of redox reactions, which is a form of chemical potential energy. We know right now that a redox reaction involves a reduction and oxidation, which involves a transfer of electrons from the thing that is being oxidized or losing electrons to the thing that is being reduced or gaining electrons. In a voltaic cell, electrons or electricity pass from the reducing agent to the oxidizing agent. Remember that the strongest oxidizing agent gets reduced and the strongest reducing agent gets oxidized. So through an external circuit is where these electrons pass rather than passing from one substance to another. So if you want to try to think about it, what's going on here is instead of just mixing something in the same beaker, we're finding a way to force the electrons to travel along an external circuit, along a wire, so that we can actually capture the energy that's being created by the flow of electrons, or electricity for that matter. So the two halves of a voltaic cell, what we call half cells, and that should sound similar to half reactions, and that's exactly what we have going on, is that there is a half reaction on either side of the cell, the voltaic cell, and there's a half reaction, which is a reduction, and a half reaction, which is an oxidation. So we have the oxidation half cell and the reduction half cell. These two half cells are separated by a porous boundary, which permits ions to move between the two solutions. I'm going to talk about these briefly by looking at a diagram shortly. So before we get into that, let's just quickly talk about something called cell notation. So a cell is the structure of the redox reaction that we're going to be using to capture the flow of electrons. So a cell is represented by something called cell notation. And this is what we see with cell notation here. So there's our cell notation for a specific cell. In this case, we would call this a copper zinc cell. And what we have going on here is we've got one side of the cell over here, which is involving copper ions and solid copper. And over here, we have the other side of the cell, which is involving zinc ions and solid zinc. Now, just to give you an introduction to what's going on in here, this vertical line here and here represents a phase boundary. And what we mean by phase boundary is a boundary between states of matter. In this case, this boundary is between solid copper and aqueous copper. So remember that aqueous means dissolved in water. So aqueous copper is copper ions floating around in that solution. So then another way to put this is the interface between the electrode and the electrolyte. The electrode being the solid part of this and the electrolyte being the solution part of this. The double vertical line indicates a physical boundary rather than a phase boundary, a physical boundary. So this is what we call the porous barrier or the porous cup, or we'll call it a salt bridge later on. This actually means that the two half cells are physically separated from each other, not just by phases, but by physical separation. And each side of the double line represents a half reaction. So this is an example of what we would call a wet cell. So this is a form of a cell that's powered by a redox reaction. And I really quickly want to run you through how this works. Remember, this all has to do with redox reactions. So there's going to be an oxidation and there's going to be a reduction. In order to figure out which is an oxidation and which is a reduction, we need to consult our table on page 7 of our data booklet. So if you wanted to grab your data booklets right now and open up to page 7, you can have a quick look at what's going on here. So I'll just give you a second to grab those. If you need to pause, you can pause right now. So what's going on is we have two half cells here. Over on this side, we have a half cell, and over on this side, we have a half cell. On the left side, we have a copper and copper ion half cell, and we have a zinc and a zinc ion half cell on the right-hand side. What we have is a beaker on each side with a solution inside each beaker, an electrode that is dipped into the solution on each side, and the two electrodes are connected by a wire in between. The last piece that we have is something called a salt bridge, and the salt bridge it forms that porous boundary that we talked about, that physical boundary. So we could kind of assume that there would be a double line in between here. And the porous boundary here in this case, or the salt bridge, is filled with sodium nitrate. Both sodium ions and nitrate ions are very unreactive, so there is no chance in this half cell that they're going to take over the reaction by becoming the strongest oxidizing or the strongest reducing agent. So we have a copper electrode on the left side dipped into a copper nitrate electrolyte solution. Again, nitrate ions, meaning that it's not going to participate in the reaction. On the right hand side, we have zinc electrodes and a zinc nitrate electrolyte in here. So what we need to do is we need to try to figure out what's going on in this cell. The whole goal of this is to generate a flow of electrons from one side to the other and have those electrons flow along a wire. Now this is just simply a wire here, meaning that the electrons can flow across it in whatever direction, but we're not really doing anything with it. If we were to put some sort of a circuit in here, what would end up happening is we could then start to use the flow of electrons to power something along that circuit. So think about, for example, your calculators, which are powered by batteries. If this becomes your battery in this location here, then what's going to happen is as the electrons flow from one side to the other, the electrons are going to flow through that entire circuit or combination of circuits that is your calculator, and your calculator is going to hook up or power up. However, we don't have something like this going on with our calculator. We've got batteries that are wet cells, or dry cells actually, that work slightly differently than what we have here, but the principle is still the same. So how we work with this kind of cell to figure out how it operates in particular is we need to go to our table of relative strengths of oxidizing and reducing agents on page 7, and we need to locate our strongest oxidizing and strongest reducing agents. Now here's a hint. When you know what these half cells are, you can get a sense to what's actually doing the reacting. So in this case, we've got copper ions and solid copper, zinc ions and solid zinc. So going over to my table of relative strengths, what I can see on here is we can find the zinc ions, and I won't be able to draw on this, but we'll be able to find them relatively quickly. Here are our zinc ions down here and our solid zinc, so oxidizing agent, reducing agent. And to find our copper, there's our copper ions and our solid copper. So if we look at just copper ions and zinc ions as our oxidizing agents, our copper is going to be our strongest oxidizing agent. If we look at solid copper and solid zinc as our two reducing agents, because the zinc is on the furthest down on the right, it's going to be our strongest reducing agent. So going back to this diagram here, this becomes our strongest reducing agent. And this over here becomes our strongest oxidizing agent. Our strongest oxidizing agent gets reduced, and our strongest reducing agent gets oxidized. So our strongest oxidizing agent gets reduced, meaning that copper ions, and I apologize for the writing, but I'm drawing with my mouse right now. So Cu2 plus and 2 electrons turn into solid copper. Okay, that's our reduction. Over on this side, we have our zinc turning into zinc 2 plus, again, apologies for the writing, and 2 electrons. So what's happening here then is that oxidation is occurring over here because the strongest reducing agent gets oxidized. Reduction is occurring over here because the strongest oxidizing agent gets reduced. We know that oxidation is a loss of electrons, and we know that reduction is a gain of electrons. So what's happening in this voltaic cell is that electrons, okay, are being lost over here. So we have electrons that are moving up the electrode, okay, being lost at the oxidation half cell. Those electrons are moving along the wire towards where they are going to be gained, because gain of electrons is reduction. So those electrons that we're talking about are going to be gained here at the electrode, at the copper electrode. So we've got electrons flowing from the strongest oxidizing agent, or strongest reducing agent, which is getting oxidized, to the strongest oxidizing agent, which is getting reduced. What's happening is we're losing electrons is solid pieces of zinc are breaking off of this zinc electrode, okay, and they're turning into zinc 2 plus ions. Okay, and what's happening over here is as those two electrons move their way along the wire and get to the copper electrode, the two electrons are actually going to become part of, or join up with, the copper ions that are in this electrolyte solution. So those copper ions are going to come on, gain 2 electrons, and attach to this electrode. So what's happening over here on this side is that these zinc we're creating zinc ions over on the oxidation side, and we're losing copper ions on the reduction side, and actually making copper, solid copper, on the copper electrode here. So what we're going to be seeing over on this side is we're going to lose mass over on this side, and we're going to gain mass on the electrode on this side. Now, the one last set of terms that I have to introduce to you, and I've kind of introduced them to you already, is the terms cathode and anode. When we're talking about a voltaic cell or an electrolytic cell later on, each has a cathode and an anode. And I told you at the beginning of the unit, there's 2 things you're going to remember. Leo goes Gur, and that the strongest oxidizing agent gets reduced at the cathode, and the strongest reducing agent gets oxidized at the anode. So oxidation occurs at the anode. Oxidation is a loss of electrons. So from the anode, electrons move along the external circuit to the cathode, where they are gained at the cathode. So just to continue on with that point, just to summarize everything I've drawn in really bad writing on the last slide. According to electron transfer theory and the concept of relative strengths of oxidizing and reducing agent, we know that the strongest oxidizing agent in the cell undergoes reduction at the cathode, and the strongest reducing agent in the cell undergoes oxidation at the anode. So the cathode is the electrode where reduction occurs, and the anode is the electrode where oxidation occurs. So this little bit right here becomes very important. The strongest oxidizing agent present in the cell always undergoes reduction at the cathode, and the strongest reducing agent present in the cell always undergoes oxidation at the anode. So as a result, Electrons are released by the oxidation, or LEO, travel along the wire from the anode, where the oxidation occurs, to the cathode, where the reduction occurs, and that's where the electrons should be gained. So this diagram sort of fills in exactly what's going on. The one piece that I didn't explain to you at this point was what exactly, I guess there's two pieces here. The charges of the anode and the cathode, and you'll notice the cathode in a voltaic cell is positive, and the anode in a voltaic cell is negative. Now I've said that very specifically, and when we get to electrolytic cells a bit later on, you'll understand what's going on. By the way, this is a different cell. We're not doing zinc and copper anymore. Be aware of that when we've switched over to silver and copper, which changes things. In this case, our copper has now become our oxidation half cell, or our anode half cell, and the silver has become the reduction half cell. The other thing that I didn't explain on the last example is what happens, and I'm gonna switch back to that right now. What happens is that as this cell runs and the electrons are flowing from the anode to the cathode, what you can see happen is that this side is gradually becoming more positive. So it gradually becomes more positive. Okay. The reason for that is that it is gaining these zinc 2 plus ions. The solution is gaining zinc 2 plus ions as this side is losing electrons. Over here, this side is gaining negatives and gradually becoming more negative. Okay, the reason it's becoming more negative is because it's gaining those electrons, and that those 2 plus ions that are floating around in this solution are becoming part of the electrode, therefore losing positives. What's going to happen is that gradually this side is going to become more positive, this side is going to become more negative. And eventually, if we let that happen with nothing else going on, these charges build up so much that the cell will stop working. So that's where the salt bridge comes into play. And I'm going to show you this because it'll be a little easier on this diagram right here. So you'll notice that we've got a loss of electrons happening over here. So this side is gradually becoming more positive. And this side over here is gradually becoming more negative. So in order to combat this, what the salt bridge does, remember the salt bridge is filled with something that's very unreactive, like in this case sodium nitrate. So the nitrate ions that are negative are going to move out of the solution in the salt bridge and into this solution on this side. So bringing more negative to this side to try to balance out the buildup of positive over here. The other thing that will happen is some of these copper ions will start to migrate into the salt bridge, removing some of the positive. So we're going to try to combat the buildup of positive on this side by adding negative and removing positive. I hope that makes sense. Over on this side of the cell, what's going to happen is that we're going to end up seeing a buildup of negative. So how the salt bridge combats that is some of the sodium ions, which are positive, will move into this side of the cell. So combating the buildup of negative by adding positive. And then some of the nitrate ions are going to move up into the salt bridge. So combating the buildup of negative by removing negative. So if we have a salt bridge present, everything is going to balance itself out really nicely, and we're going to end up not building up too much charge on either side. We've got a flow of electrons going on through here, and if we were to put something in that spot, maybe a voltmeter, we could actually measure the flow of electrons through there. This diagram here, which I've accidentally cut off at the bottom, is a good one for you to go through and have a quick look at some point, and maybe when I'm back, we can have a quick look at it together and summarize things. We can represent the cell here in this diagram with a net equation created by adding the two half cells together. So here is our cell notation for that particular cell. And we know that at the cathode, which is being reduced, which is gaining electrons, we have silver ions turning into solid silver by gaining electrons. And at the anode, which is being oxidized, we have copper, solid copper turning into copper ions by losing 2 electrons. As we've done all the way through this unit, the number of electrons lost must equal the number of electrons gained, and so we need to multiply this side by 2. And when we cancel out the electrons that we have in both of the half cells, we end up with our net cell reaction. Something to note here, an inert electrode can be used in situations where we don't have a solid electrode that would work well. So for example, if you recall, looking at our table here, some of these particular combinations of strong oxidizing agents that we've looked at before, for example, like the permanganate, acidified permanganate ions, or maybe the acidified dichromate ions, those are solutions, acidified solutions, which are going to act as the strongest oxidizing agent, but really don't contain a solid metal in any way. And so what can happen in those kinds of situations is we can use an inert electrode, something like graphite or pure carbon or platinum, which are inherently unreactive, and we can use them if our strong oxidizing agent or strong reducing agent is not a metal. So like I said, like an acidic dichromate solution, for example. And so what we would do is we would plop that inert electrode into that solution so that it can behave like the strongest oxidizing or strongest reducing agent. And all that inert electrode does is it becomes a solid conductor that doesn't interfere with the reaction, but all it allows for is a spot to connect the wire and a location for the half reaction to occur. And what we mean by that is a space for electrons to attach to or be removed from, depending on the situation. So, in summary, in a voltaic cell, one half cell is the site of oxidation. So loss of electrons is oxidation. And we call this, in a voltaic cell, an anode. The oxidized species in this case is the reducing agent, or Ra. And oxidation we know is the loss of electrons, and in this case electrons flow away from the anode through the wire because they are being lost at the anode. If the reducing agent is a metal, it will turn into cations and flow away from the anode in the solution towards the salt bridge. The other half of this voltaic cell is the site of reduction, and we call it the cathode in this case, and it has a positive charge associated with it, or it is the positive part of the cell. This reduced species, and we say species because it could be an ion, or it could be a metal possibly, or something along those lines. It's called the oxidizing agent. We know that the oxidizing agent gets reduced, and reduction is the gain of electrons. And in this case, electrons are flowing towards the cathode through the wire. If the cations are being reduced, then they flow towards the cathode through the solution. So in our example with the silver ions right here, the silver ions that were in this solution become part of the electrode as they gain electrons. The salt bridge or porous cup, and you'll see a porous cup on your LSM for this concept, or for the first LSM in this concept. A porous cup is just simply a ceramic cup that is porous enough that ions can move into and out of it. So we don't need two beakers to create that physical boundary. We can create the physical boundary by filling the porous cup with a solution and dipping an electrode into it, and then placing that porous cup in a beaker and dipping an electrode into that beaker, and then connecting the two electrodes with a wire. So the salt bridge or porous cup allows ions to flow from the anode to the cathode, and if the ions could not flow, we get a charge buildup, which would stop the reactions really quickly. And we know that electrons flow through the exterior wire, and we often put a voltmeter in the circuit or something else in that circuit to take advantage of it. There are a couple of videos here that I'll share with you later on. This video is actually a quick rundown of what happens in a voltaic cell, and you can find it on the Google Classroom. It's embedded in our unit for that. So that is the end of our quick introduction to voltaic cells. Your sub has information for you on what I'd like you to do to follow up with this section. And when I get back, I will spend time running this through with you if you need it, just to make sure that you are aware of exactly what's going on. As always, make sure you go through and mark any things that aren't making complete sense, but do try to do what I assign you to do. Otherwise, we're going to end up falling behind, and if I have to go quickly at some point, you may not get caught up. So, hope to see you soon, and thanks for listening.